everybody, 7.3 trigonometric substitution is really a combination of using what we learned in 7.2 and using those reduction formulas, as well as using our U substitution method. Okay, we're going to use Pythagorean identities such as sine squared x plus cosine squared x is equal to 1, as well as 1 plus tan squared theta, or x, is equal to secant squared x. Okay. So there's going to be a few different scenarios that we look at, and I'll show you examples for each of them. The first one is if it looks like the square root of 1 minus x squared, as an example, or a minus x squared. So for this one, first of all, this integrand is defined for values between -1 and 1. Right, because of the domain restriction that we would have there. So we are allowed to set x equal to sine theta. Because sine theta would stay between -1 and 1 as well. That's the background information for why we are allowed to do this. And theta, of course, in this case is between -pi/2 and pi/2. Ultimately, that's background information. It really doesn't matter so much, but it's helpful to understand why this is allowed. So from here, right, we really are looking to substitute for this square root of 1 minus x squared. That's our ultimate goal. So the book kind of cuts a little corners in terms of the notation, but if I'm naming x equal to sine theta, then the square root of 1 minus x squared is first of all equal to the square root of 1 minus sine squared theta, yep, which is also equal to the square root of cosine squared theta, which is ultimately equal to cosine theta, okay? So from here, now we're actually ready to do our substitution and derive and find all of our pieces. So we named x equaling sine theta. We then would know that dx is equal to cosine theta d theta. Right, so we have all the pieces that we need so that we can then say that this integral that was originally the integral of square root 1 minus x squared dx, well, this is equal to the integral of cosine theta, and then the dx would be replaced with cosine theta d theta. Okay. So this is equivalent to the integral of cosine squared theta d theta. And now you can refer back to your table of trig integrals and use the appropriate one. So the second one there, or number 10, cosine squared theta, is equal to, the integral of it is equal to 1/2 theta plus 1/2 sine theta cosine theta plus c. Okay. And finally, we do need to convert back. So sometimes we'll have all of the information, sometimes we'll have to draw a triangle up to pull what we need. So in this case, my theta, I don't exactly have that, right? But if I know that x equals sine theta, well, then theta equals sine inverse x. So I have 1/2 sine inverse x plus 1/2, again, x is sine theta, so x, cosine theta was the square root 1 minus x squared plus c. So everything here is rewritten with respect to x, and that would be my final answer. So the second example looks completely different, right? But it still has essentially a square root in it. And it has that same idea of a 1 minus x squared, but now it's in a 4, or an a squared minus x squared is what we're looking to do. So we first need to name x. Just like the previous one. We need to pay attention to what's my a going to be, and therefore how do I completely substitute things out. So I would have to rewrite the 4 so it's a quantity squared. So that's what makes my a 2. And therefore my x is equal to 2 sine theta. And my dx is equal to 2 cosine theta d theta. Okay. And my square root of 4 minus x squared, that's the part that I'm focusing on, right? Everything in that denominator except for the cubed. That's equal to, first I like to write it as square root of 2 squared minus x squared, or the square root of 2 squared minus 2 sine theta squared, or 4 sine squared theta. Right, so this is equal to the square root of 4 cosine squared theta, or 2 cosine theta. Okay. So now, taking all of this and substituting it in, right, I have an x squared in my numerator. Well, x is 2 sine theta, so my numerator is 4 sine squared theta. My denominator, I have that 4 minus x squared square root, which is equal to 2 cosine theta, and I have that cubed. And then my dx is equal to 2 cosine theta d theta. Usually when I'm plugging all of this back in, things do simplify for themselves. So I really have integral. My coefficients, my numerator would be an 8. My denominator, 2 cubed, or 8. So that actually cancels out this time. A cosine in the denominator is going to cancel out with the cosine from the dx substitution. So I'm left with sine squared theta over cosine squared theta d theta, which is equivalent to tan squared theta d theta, integral of. I can use my reduction formula here for tan, and it's going to give me tangent theta minus integral of d theta, which is tangent theta minus theta plus c. In order to convert back, I don't have a tangent theta up in my substitution work. So I'm going to draw out my triangle. Put my theta there. So I know that sine theta equals x over 2. Okay. So sine opposite over the hypotenuse, then I can fill my triangle in. I chose to go with x over 2 and a 1 and a square root 4 minus x squared over 2. Obviously, I could multiply everything by 2 and that all cancels the denominators out, but that's just what I did. Okay. Anyways, I did this so that I could figure out my tangent, and my tangent then becomes opposite over adjacent, so I'm going to have x over square root of 4 minus x squared. So there's my tan theta, and then my theta is equal to, if I take the x equaling 2 sine theta and rewrite it, then sine inverse of x over 2 plus c. Okay, example 3. So now we have it in a format of x squared plus a squared. Right, so it's a little bit different. We don't have the subtraction. So now we're using 1 plus tan squared theta equals secant squared theta. This relationship in order to use substitution here. Okay, same idea. I need to figure out what my a is, so then I can then replace with an x equaling a tan theta. So in this example, I have a common factor of a 4 that I need to pull all the way out. So if I factor the 4 out and then I square root it, I would end up with a 2 in front of my integral. So my a is square root of 5. And therefore my x is square root of 5 tan theta. My dx is square root of 5 secant squared theta d theta. And I need to replace the square root of x squared plus 5. So I have root 5 tan theta squared, or 5 tan squared theta, plus 5 is equal to square root of 5 secant squared theta, which is where we would get root 5 secant theta. Okay, so now we have all the pieces we need. So 2 integral of root 5 secant theta times root 5 secant squared theta d theta, to substitute for dx, which is equal to root 5 times root 5. I can take a 5 out in front, so I have a 10 integral secant cubed theta d theta. So reduction formula would give me 10 times tan theta secant theta over 2 plus 1/2 integral secant theta d theta. Okay, also in that trig table, from here I would then have 5 tan theta secant theta plus 5 ln of, I don't need my absolute values because of the domain, secant theta plus tan theta plus c. Final step, replace all of the theta terms with x terms. So I need my triangle again. I know that tan is equal to x over root 5, so opposite over adjacent. So I have x and I have root 5 here. And then I would have square root of x squared plus 5 squared. So for my answer I have 5. Tan theta is x over root 5. Secant theta is going to be root x squared plus 5 over root 5 plus 5 ln of square root x squared plus 5 over root 5 plus x over root 5 plus c. So that's my final answer, but of course I can clean it up a little bit. 5 divided by root 5 divided by root 5, that's 1. So this is equal to x square root of x squared plus 5 plus 5 ln of root x squared plus 5 plus x over root 5, common denominator, plus c. Okay, we have 2 more examples here. Here I have an x squared minus an a squared format. For these examples, I am also using secant squared theta minus 1 equaling tan squared theta now. So I've just rewritten it a little bit from what we had before. Okay. So again, I'm looking for that a, I'm looking for now x equaling a secant theta. So in this case, my a is going to be 3. So my x is equal to 3 secant theta. My dx is equal to 3 secant theta tan theta d theta. Okay. My square root of x squared minus 3 squared is square root of 9 secant squared theta minus 9, which is equal to 9 tan squared theta, square root of that, which is equal to 3 tan theta. You can jump right to that if you're comfortable. I just like to show all of the steps for how square root of x squared minus 3 squared becomes 3 tangent theta. Okay. So now rewriting my integral, dx is in the numerator, so 3 secant theta tan theta d theta. I have an x squared out in front, so I have a 9 secant squared theta times square root of x squared minus 9, or 3 tan theta. Canceling whatever out that we can. This tan and tan are gone. Right. The 3 and the 3 are gone. A secant with one of the secants are gone. So I really just have a 1/9 integral 1 over secant, which is cosine, theta d theta, which is 1/9 sine theta plus c. Wow, doesn't get easier than that at the end. The only thing I need is to go ahead and come up with sine theta with respect to x, so I'm going to draw out my triangle. All right, so I know that secant theta equals x over 3, so cosine equals 3 over x. So I have that, and then I would have, of course, square root of x squared minus 9. So my sine is the square root of x squared minus 9 over x. So my final answer is the 1/9 square root of x squared minus 9 over x plus c. Last example here involves completing the square so that we can essentially force this same substitution. We're going to complete the square and rewrite the completed square as a square root. So we're going to use a fourth power in order to get our square root. Okay? So x squared minus 6x plus 11 would be completed by saying x squared minus 6x plus 9 plus 2, or x minus 3 squared plus 2. Obviously, it's all still squared. Okay. So then I'm going to name u equal to x minus 3, and du is just dx. So this is our first level of substitution. So that means that we are equal to du over u squared plus 2 quantity squared. Okay. So then this example in the textbook, I think if you're following along in the book, was a little bit quick to jump to the conclusion without explaining it very well. So, of course, our u is going to be written in terms of some kind of trig, but how do we get there? So I looked at this and I said, well, so this is equivalent to u squared plus 2 all squared. Right, but we really need to have this square root. So if I want to have a square root, if I want this to be equivalent, then I would have to write it as the square root of u squared plus 2, right? Square that, so that it's you know, not changing anything. And then it's squared again in order to stay equivalent. Okay. So this is an equivalent form, and now I can focus on the fact that if my u and my 2 are in there, like the previous examples, I would need to name my u root 2 tan theta. My du then could be root 2 secant squared theta d theta. And I'm going to come back over to the right side over here to rewrite what I need. So then I would say that the square root of 2 tan squared theta plus 2 is equal to square root of 2 secant squared theta, or root 2 secant theta. Okay. So finally I can actually do my substitution, and I'm going to have, for my du up top, I have root 2 secant squared theta d theta. down below for my u squared plus 2, that's equivalent to root 2 secant theta to the 4th power, right? We squared the square root, and then there was already the square in there. So that's the part that I think that the book kind of jumped over, the 4th power. Where does that come from? All right, so now I can clean things up, simplify them. I have a root 2 over a root 2 to the 4th. So I kind of have a root 2 to the 3rd on the bottom, or a u to the 3/2 power, or however you want to simplify that, but ultimately it's 1 over 2 times root 2. Then I have secant squared theta d theta over secant to the 4th theta d theta, or 1 over secant squared or cosine squared. So reduction formula would bring me to theta over 2, but multiplied by that coefficient that I already have. So I'm going to have a theta over 4 root 2 plus a 1 over 4 root 2 sine theta cosine theta plus a c. I need sine and cosine of this theta, so I'm going to draw my triangle. I know that tan is u over root 2. So I have those two relationships. Then this would be square root of u squared plus 2. So my sine theta and I also have to go from u to x, right? So I can do that over here just so that I don't have to do double substitution at the end. U is the same. I'll do that in blue. U is x minus 3. Oops, not blue highlighter. So I have an x minus 3. I have a root 2. And I have a square root of x minus 3 squared plus 2. Right, so my final answer is going to be, in order to get this theta, theta is equal to tan inverse of x minus 3 over 2 over root 2. So I have 1 over 4 root 2 tan inverse of x minus 3 over root 2 plus 1 over 4 root 2 times sine theta, which is x minus 3 times the square root of all that. I'm sorry, x minus 3 over the square root of all that. And my cosine is root 2 over the hypotenuse plus c. Okay, so I can lose the root 2's. The square roots would cancel when I simplify this. So my final answer, 1 over 4 root 2 tan inverse of x minus 3 over root 2 plus x minus 3 is my numerator, 4 times, multiplying these square roots together, the square roots cancel. Remember, we completed the square in the beginning, so it's really just x squared minus 6x plus 11, and then plus c at the end. So that one was tough. It was technically a double substitution. We had to complete the square in order to kind of force this trig substitution pattern. And then at the end, we need to then remember that it was that double substitution and get all the way back to our x's.